In this video, we will be examining the mechanisms by which elimination reactions occur. As we saw in previous videos, nucleophilic substitution can proceed by two mechanisms, and elimination is just the same. It has both an E1 and an E2 mechanism. Also similar to nucleophilic substitution, SN1 versus SN2. E1 denotes that the rate determining step is unimolecular, meaning that there's one molecule involved in the rate determining step. And E2 reactions in their rate determining step are bimolecular. So there's two molecules involved in the rate determining step. And we will examine both the E1 and the E2 mechanism, examine regioselectivity, stereoselectivity, and any issues that can occur or any challenges that can occur for either one of these mechanisms. So let's start by examining the E1 mechanism. So in general, the E1 mechanism, we'll start with the same kind of drawing that we looked at before. We'll have A on one side, B on the other, and I'll draw the mechanism arrows in green. In an E1 mechanism, similar to an SN1 mechanism, we are going to form a carbocation intermediate. So the first step is this Ca bond is going to break. We are going to lose A minus, and we will be left with the carbocation intermediate with B still attached. Finally, in the second step, we will have some kind of nucleophile, whether it be a base or some kind of Lewis base. We'll have a nucleophile come in. It'll pluck off B. This bond will be pushed into the CC single bond, forming a CC double bond. We will lose nucleophile B, or BNU. Actually, let me write that how it would form, how it would be written as an ionic salt. So we would lose B and U, and this might have a plus charge depending on the charge of the nucleophile. And we would be left with the C double bond C. So overall, the mechanism, we have the loss of the A, the loss of the leaving group, and then we have the nucleophile attacking B and pushing the electrons in the bond. We push these electrons in the CB sigma bond. We push it into the CC area to make a CC double bond. What we see is that this process right here, just like in SN1 mechanism, this is the rate determining step. So what we see is our rate is K and is proportional to the starting material, whatever this AB is, whatever the starting alkane is. And since it is only dependent on A leaving, this is going to be indicating that it's a unimolecular rate law that we only go based on the concentration of the starting material. So let's look at what this would look like for both dehydrohalogenation and for dehydration of alcohol. So let's examine dehydrohalogenation first. So this is dehydrohalogenation. So specifically, dehydrohalogenation, we have CC, and then we have on one carbon we have a hydrogen, on another carbon we have an X. Now the first step is, as described before, we have X leave. We're going to lose that leaving group, and we will lose a net X minus, and then we will be left with the carbocation intermediate. And we have H on this carbon here. In the next step, we have some kind of exogenous base made that might be X minus, that may be solvent, that may be water. Either way, it's going to be some Lewis base with a lone pair is going to grab this hydrogen and push the electrons into the double bond, or into forming the double bond. We will lose, as written, we lose BH plus, but that totally depends on the charge of the B. If this was X, this would be minus HX. So it totally depends on what the charge on B is. And what we are left with is C double bond C. So let's look at an example of this. So let's say we have this type of alkyl bromide we have tertiary alkyl bromide. And usually these dehydrohalogenations, if they are truly following an E1 mechanism, this might be a solvolysis type reaction. So say we're doing this in water, and there's heat. So the first step of the reaction would be loss of the bromide. So we lose bromide, and we form this tertiary carbocation. Now, as you can see, we have an option of where to form the double bond. We could form a terminal double bond or an internal double bond. Now, as we saw in the last video, we know that Zaitsev's rule will predict that we will form the more substituted double bond. So if we pluck off the internal hydrogen, we would instead form a tri-substitute alkene. So that's what we're going to do. I'm going to draw bromide plucking off the exogenous hydrogen. You could also draw water plucking off the exogenous hydrogen. It doesn't really matter as long as you have some Lewis base. We have bromide come in, pluck off the H, push into the CC bond to stabilize that carbocation and form the double bond. We would lose an equivalent of HBr, or if you used water, you'd lose an equivalent of H3O plus, which upon reaction with Br minus would form H2O and HBr. What we're left with is the tri-substituted alkene. Plus an equivalent of HBr, H3O plus, depending on what you use to pluck off the hydrogen. So this would be the dehydrohalogenation. So this is a two-step mechanism. First, we lose our our bromide or our halide, and then the second step, we use some base to pluck off a hydrogen to form the alkene. If we are examining the dehydration, however, we do have an extra step, and we did see this earlier in nucleophilic substitution, both in Chapter 5 and Chapter 6. Let's say we we're examining, instead of the tertiary alkyl halide, we were examining the tertiary alcohol. So we can't just have OH leave. That's not going to happen because OH is not a good leaving group. And what we saw in previous chapters is that we are going to instead have protonation of the alcohol first to form a good leaving group, and then water will leave. So as we saw, this requires an acid catalyst, so I'll say H2SO4, which I will abbreviate as HA. And the first step of this mechanism is going to be deprotonation protonation of the alcohol by the acid. So you have OH get protonated, we'll lose A minus. And then we will form the protonated alcohol, the alkyl oxonium, and this is where we will lose water. So this is when we will form the carbocation intermediate. So we've lost water, that's our loss of water, and that will generate the carbocation intermediate, our tertiary carbocation, very stable. Examining this is the rate determining step right here, the loss of water. So we can write a rate law of the rate is K, and then that's dependent on the alkyl oxonium ion, whatever that oxonium intermediate is. It's going to be, the concentration of that is going to dictate the rate law. So this is also dictated by the strength of this acid. So this is why we need strong acids like H2SO4 or H3PO4 to protonate the alcohol. In the final step, we have something base deprotonate the carbocation alkane. I'm going to use A minus just to regenerate the HA. In general, it could be water, but in general, we're removing water from the system because that'll force the reaction backwards. So as we see, this regenerates HA, which would be used up back here. This is why it's a catalyst. And that would, in turn, form the tri-substitute alkene. So, the issue that we run into with dehydration and dehydrohalogenation in an E1 mechanism is the same issue we ran into with an SN1 mechanism, which is that we generate carbocation intermediates. And carbocation intermediates, as we've seen, can rearrange. So, for instance, if we had instead this alcohol, and we add H2SO4. Here, let's make this tertiary. And heat. Now, the first step would be the same. We'd protonate the alcohol. We generate HA. We'd lose HA. Sorry, A minus. We lose A minus. And we'd generate the alkyloxonium intermediate. And in the next step of the mechanism, we would see the water leave. So far, the mechanism has started out exactly the same. We haven't changed anything, so we'd lose water. And we're left with the secondary carbocation. Now, this is good. Secondary carbocations are stable. However, we see if we do a methyl shift, we do a methyl shift from this tertiary position, actually quaternary position, to the secondary position, we will instead generate a tertiary carbocation. So what that looks like, we're going to do a methyl shift. We're doing a carbocation rearrangement, just as we saw in the last chapter. And what we see now is we have a tertiary carbocation. So we went from a secondary to a tertiary carbocation, which is more stable. Remember, if we can generate a more stable carbocation through hydride shift or a methyl shift or a alkyl shift, we will do the rearrangement. They are fast, they are favorable, and they will stabilize the carbocation intermediate. Now we have the most stable carbocation. We can do the elimination. Again, we can generate the terminal alkene or the internal alkene. Zaitsev's rule dictates that we will generate the more substituted products. So if we pluck off this internal hydrogen with an exogenous base, I'm saying A minus just to regenerate HA, we see that we would, so we lose HA, and we would generate the tetrasubstituted alkene in this process. Whereas if we looked here, if we were to do this rearrangement, if we were to do this elimination without rearrangement, so we would do this here, there is no hydrogen at this position to pluck off, so we would necessarily have to pluck off this hydrogen. And so without rearrangement, we would be left with a monosubstituted alkene that is terminal. Tetrasubstituted is way more stable than monosubstituted. Plus, so through the rearrangement, we have stabilized the alkene intermediate. So again, carbocation rearrangement can and will occur if it can stable the carbocation intermediate that is formed in the process of an E1 elimination reaction. So just watch out for that when you're doing E1 reactions, that methyl shifts and hydride shifts can and will occur if it will stabilize the carbocation intermediate. So the next type of reaction, the other type of reaction that we'll be examining is going to be the E2 mechanism. So as we saw with SN2, E2 is bimolecular in the rate determining step. So this is usually a concerted mechanism. So again, we'll start with the same structure over here. We have H, I'll draw an H here. And I'm drawing this X in a particular way. We'll call this X just to indicate that it's a dehydrohalogenation. This can happen with alcohols. There's just a few more specifics. As we see, the leaving of the leaving group and the plucking off of the hydrogen will occur in the same step. So what we see is if we have exogenous base with some lone pair, whether it be negative or neutral, this will pluck off the H. This will push into the double bond, and this is what will push out the X. So this is a three-arrow mechanism. What we see is we lose H base, and I'll just call this a plus charge. Again, it depends on the charge of the base. And we lose X minus, and our net result is the same. We end up with the alkene. An example of what this reaction would look like, say we have this secondary alkyl chloride. We have hydrogen. Say I add sodium methoxide, and this is usually in the alcoholic version, the alcoholic equivalent of the, or counter acid of the base. So this would be a methanol. What I would have here is I'd have methoxide, which is right here. I'd have methoxide come in. This would plug off the hydrogen. This would push. This would push out the chloride. So what I'd be left with is the alkene, and trans would be preferred because trans is more stable than cis. I'd be left with methanol, which is formed right here, and chloride, which is going to be counter-ion by the Na. So we'd be left with NaCl just to balance these. These would just be to balance the equation here. So we'd be left with the alkene. So this is a concerted one-step mechanism. Things to note about E2 reactions: they always require strong base. Almost always require strong base, depending on the acidity of the proton that we're plucking off. It may not need to be such a strong base as methoxide, but in general, it requires a strong base. It usually requires heat. Just like an E1 mechanism, it usually requires heat. And since this is a concerted mechanism, there's no possibility for rearrangement. There is no carbocation form, so there is no possibility for rearrangement. And it does follow Zaitsev's rule, so we are still going to pluck off the hydrogen that makes the more substituted product. We can see this for alcohols. This is less common in E2 reaction, but we do see it for primary alcohols. So say we do the dehydration in H2SO4. I'm not going to draw this mechanism, but we'd have the alkyl oxonium intermediate. And since this is primary, we can't really form a stable carbocation. So what we will see is we will pluck off the hydrogen and push out water in a concerted mechanism rather than in two separate steps. We can't form the primary carbocation. That would be too unstable. So we do end up with the same type of reactivity. We do end up with the ethene from ethanol. It just happens in a concerted fashion. So let's examine a few complications that occur with E2 mechanisms. So we saw that in E1 mechanisms, one of the complications that occurs is carbocation rearrangements. Now, there's no possibility for carbocation rearrangements in an E2 mechanism, but we do run into other issues. So let's look at this reaction here. So this is a cyclohexylbromide, and say I add sodium methoxide and methanol. Just like in previous reactions, we see that there's two hydrogens we can pluck off. One will form the di-substituted product, and one will form the tri-substituted product. So Zaitsev's rule tells us that we will preferentially form the tri-substituted product plus an equivalent of not HBr, NABr, and methanol. So we call this product that follows Zaitsev's rule, we call this the Zaitsev product because it follows Zaitsev's rule. One complicating factor is what happens if instead of sodium methoxide, we use sodium terbutoxide and T-butanol. Now, just for those who need a refresher, terbutyl looks like this. This is terbutoxide. So, as compared to methoxide. So, comparing methoxide to terbutoxide, we see that terbutoxide is a much, much bulkier, sterically hindered, larger base than methoxide. So what we see is that if terbutoxide was to try and come in and pluck off this hydrogen, it's blocked by this methyl group. So this won't actually occur. In fact, terbutoxide is so bulky that it needs to form the anti-Zaitsev product. So what we see is when we use terbutoxide as a base, we form the anti-Zaitsev product, or what's known as the Hoffman product. So the Hoffman product is the opposite of the Zaitsev product. It's when we form the less substituted alkene. So Zaitsev product is more substituted, where the Hofmann product is less substituted. And the Hofmann product can be forced by using bulky bases. So this is something like terbutoxide. This is something like isopropoxide. Other common bases, DBU is a bulky base. Pyridine is a bulky base. All of these are going to force the Hofmann product because they are sterically hindered. They can't get in. They can't sterically get in past this methyl group to pluck off that proton, so they're going to go to the less substituted side. There is also some stereoselectivity that is imparted in these E2 reactions, less so that affects Zaitsev versus Hofmann. That's going to be dictated by the base. But stereochemistry and stereoelectronics of these starting materials will affect the rate of an E2 reaction. So let's look at these two starting materials. So we have a T-butyl and a bromide, and versus, so this is the cis isomer versus the trans isomer. So if we're to draw chair conformations for both of these products, we would have the T-butyl, which is going to, I'll draw this out, T-butyl and bromide, versus the trans isomer, we would have T-butyl, and this is drawn in such a way that T-butyl is equatorial. You can do the chair flip and see that we want T-butyl to be equatorial because it's bigger than bromide. So sterically and electronically, we would want T-butyl to be equatorial to avoid the 1,3 diaxial interactions. In the trans product, we have bromide equatorial. So let's say we add sodium methoxide and methanol to both of these reactions. So I'm going to draw the hydrogen that it would pluck off. So we're looking at this hydrogen here and this hydrogen here. So the reaction mechanism is going to be the same. So we have methoxide in both cases, plucking off the hydrogen, pushing in, and pushing out the bromide, plucking off the hydrogen, pushing in, pushing out the bromide. So our overall product of these two reactions is going to be the same. However, we see that this cis product, this cis starting material, will be much, much faster in doing elimination than the trans product. And the reason for this is because what we call this arrangement, where we have, if we were to do a Newman projection on this, we would have H pointing down, we'd have a carbon chain, and we'd have another H pointing here, and then we have bromine pointing up, we have a carbon chain and a hydrogen. This arrangement of hydrogen that's plucked off and bromine is called anti-periplanar or anti-coplanar. If we look at the orbitals that are involved in doing this mechanism, we have a hydrogen and a carbon and a carbon and a bromide. So I'll draw my hydrogen. That's going to be a 1s. Bromide is going to be a p orbital. Carbons, I'll draw these in blue. So we have some kind of sp3 hybridized orbital. We have an sp3 hybridized orbital. And then we have another sp3 hybridized orbital here. And I'm just drawing these that look like p orbitals, but these are actually sp3. So what we see is when we pluck off this hydrogen with methoxide, we're going to pluck off this hydrogen. What we see is this is the pi bond that's being formed here between these two orbitals. So this can just kind of lean over and connect. They are already in alignment to form a pi orbital, a pi molecular orbital, and this would just push out the bromine. They're already in alignment to form a pi orbital, so this is going to be a very facile, very fast process to do elimination. If instead we did not have this anti-coplanar or anti-periplanar arrangement, but we had, as is shown here, we had the bromine kind of off to the side. We have hydrogen, we have bromide, and then we have carbon and carbon. What we see is that these orbitals have to twist. They are not right next to each other. There's going to have to be some geometric twisting that needs to happen in order to form this pi bond between the carbons that are adjacent to one another. So if they are in alignment, if we have this anticoplanar alignment, we're going to have a fast E2 reaction. If they are not anticoplanar, the reaction will still happen. We still have the correct conditions for a E2 reaction. It's just going to be much, much slower. And that's because we do not have the anticoplanar arrangement. In fact, if we were to look at a Newman diagram of this one, we'd have our H pointing down, our H and our ring, and then in the back we'd have a ring, an H, and bromide. So what we see is that we have the H that we're pulling off and the bromide at an angle to one another, not coplanar. So the orbitals do not line up in a way that would make this reaction proceed quickly.